Hello everyone, this is Madhuri working as Assistant Professor in the Department of Electrical and Electronics Engineering at MLR Institute of Technology. So today I'm going to discuss on numericals on DC generators. So moving on to the first numerical in the first slide. So he has given calculate the EMF generated by a 6-pole DC series generator having 480 conductors running at a speed of 1200 rpm. The flux per pole is given as 0.012 Webers. So he is asking us to assume the conductors in the armature to be lap bound and wave bound. So before solving any problem, we have to first draw the circuit diagram for the respective question given in the respective question given. So first, as in the question, it is mentioned as DC series generator. So we have to draw. Series generator is nothing but we have a series field winding in series with the armature, which is in turn connected to load. So we know that RA is the resistance of armature conductors and the EMF is generated in the armature, and this is nothing but the resistance of the series field winding. So we have the current IA, which is equals to ISC, which is equals to IL. As all these three are connected in series, so we can assume one particular current for all the currents which are flowing across armature, series field winding and the load. So first we have to write the given data in the question. It is given like number of poles are given as 6 and the number of conductors are given as 480 and the speed is given as 1200 rpm and flux phi is given as 0.012 Webers. So he is asking us to assume that armature is lap bound and wave bound. So first, case 1, we are assuming it as lap bound armature. For a lap bound armature, we know that the number of parallel paths, that is A, which is equals to the number of poles in the machine. So number of poles is nothing but given as 6. So we're going to take it as 6. So now he's asking us to find out the EMF generated. We know that generated EMF in a DC generator, we have the formula as phi ZNP by 60A. So phi in the question is given as 0.012. Number of conductors are given as 480 and the speed is given as 1200 rpm and the number of poles are given as 6. Number of parallel paths will now be 6. So when we calculate this further, we will get the EMF generated for this kind of DC series generator in volts. So now we have to analyze the case 2. Case 2 is nothing but when the same series generator is wound in the waveform. So for wave wound armature, we have number of parallel paths is equals to 2. Using the same equation for the EMF generated across the series generator, so phi ZNP by 60A. We write the flux as 0.012 as mentioned in the question. The conductors will be 480 and the speed will be 1200 rpm and the number of poles will be 6. So with this we get the EMF generated across the armature when it is wave bound. So this is how we calculate the EMF generated in a generator for these two particular cases of lap bound and wave bound armatures. Moving on to the next numerical. A wave connected armature having 19 slots. So as given data, the slots are equals to 19 and the conductors in each slot are given as 54. So total number of conductors will now be 54 into 19. If the flux per pole is given as 0.025 webers. Number of poles are given as 8. Find the speed at which the generator gives 513 volts, and also find the speed if the armature is lap connected. So if the armature is lap connected, we know that the number of parallel paths is equals to the number of poles, which is again equals to 8. So he is asking us to find out the speed at which the generator will generate a voltage of 513 volts. So to calculate that, we use the same equation of the generated EMF equation. So here we have to find out speed. So we can rewrite this equation as Eg into 68 divided by Zp into 5. Eg is given as 513 volts. Number of parallel paths are 8. Number of conductors will be 54 into 19. Number of poles are 8, and the flux is given as 0.025 webers. Upon further calculating this, we will get the speed in RPM. 0.025. Upon further calculating this, we will get our speed in RPM. So this is how, by using the EMF equation of the generator, we can also find out, if asked, the speed with which the generator is rotating, or we can also find out any other terms which are asked in the question. This is how we calculate the speed in this particular problem. Moving on to the next numerical. So we have a 50 kilowatts 250 volts shunt generator operates on a full load at 1500 RPM. So as he has given in the question, it is a shunt generator. So I am going to draw the picture of shunt generator now. Shunt generator will have the field winding in parallel with the armature winding. Again, Ra is the resistance of the armature conductors. Rsh is the resistance of shunt field winding, and the current delivered by armature will be Ia, which will be again divided into the shunt field branch and the load. The voltage which is appearing across the load terminals can be taken as Vt. So now let us write the given data in the question. Power is given as 50 kilowatts and the voltage is given as 250 volts. Here the poles are given as 6. Number of poles is given as 6, and it is lap wound with 200 turns. So lap wound machine, the number of turns are given as 200. So now the number of conductors will be twice the number of turns, which is nothing but 400. As it is a lap wound machine, we have the number of parallel paths which will be equals to the number of poles again. Find the induced EMF and the flux per pole at full load. Given armature and field resistances are given as Ra is given as 0.01 ohms and Rsh is given as 125 ohms. So he is asking us to neglect the armature reaction here. So now we have to find out the induced EMF and the flux per pole. Induced EMF is nothing but the Eg again. So for this we will write it as Vp plus IaRa. When we write the loop equation for this particular loop, generated EMF across the armature will be delivered to the load. So we will get, and we also have brush drop, but as there is no armature reaction mentioned here, as the armature reaction is being neglected. So for now, the generated EMF, we are taking it as V, which is nothing but given as 250 plus Ia into Ra. Ra is given as 0.01 ohms. So we need to find out Ia for this particular case. So when we apply KCL at this particular node, we get IA will be equals to ISH plus IL. As we know, these are the parallel branches. So the voltage which is being appeared across the load terminals, which is given in the question as 250 volts, can be taken for calculating the ISH current. So which is nothing but 250 divided by RSH. RSH is 125. So we get it as 2 amperes. So now we have to calculate. We have been given the power and voltage which is appearing across the load. So from that we can calculate IL current also. Power divided by voltage, we get the current value. So IL will be now be 200 amps. So we got IL value as 200 amps and we got ISH value as 2 amps. So now your IA will be 200 plus 2, which is nothing but 202 amperes. So after calculating IA, we have to calculate the generated EMF. It is nothing but EG is equals to V plus IAR. V is given as 250. We got the current as 202 and the RA as 0.01. From this, we will get the generated EMF. And he's also asking us to find out flux per pole at full load condition. So we have calculated EG now. From this, EG is equals to 5 ZNP by 60A. He's asking us to find out the phi value. So we can rewrite this equation. Now we are going to, let us assume this value as y. We have got, so y multiplied by 60. We know that the number of parallel paths in a lap bound machine is equals to the number of poles here. So it is 6. And number of turns are given as 200. So turns is equals to 200. Then the conductors will be taken as twice of the turns, which is nothing but 400. Speed is given as 1500 rpm and the number of poles are 6. From this we can find out the flux per pole under full load condition. So this is how we calculate the induced EMF when the resistance of armature and the shunt field windings or the field windings are given in the question. Moving on to the next numerical. So we have a compound generator. We have a numerical on the compound generator. So compound generator delivers a load current of 50 amperes at 500 volts. So 50 amperes at 500 volts. Let us write the given data in the question again. So given data, load current is given as 50. Voltage is given as 500. RA is given as 0.05 ohms and RSC is given as 0.03 ohms. RSH is given as 250 ohms. So this is the respective given data in the question, and he has also given the contact drop for the brushes is 1 volt for each brush. So total brush drop can be taken as there are 2 brushes attached to the commutator, so we will take it as 2 volts. So now we have to assume the generator as long shunt. and short shunt, and write the respective equations and find out the induced EMF for both the cases. So before calculating it, we have got, let us draw the circuit first. We know that a compound generator is a generator where we have both series and shunt field windings connected to armature. Consider this as RSH, this as RSE, series field winding. Now this is as RA. Now this will deliver the current IA. The current flowing through the load will be IL, and the current flowing through the shunt field winding will be ISH. So we have to find out, we already have IL value. So applying the KCL again in this particular node, we know that IA will be equals to ISC, as the shunt series field winding and the armature are in series. So we can assume both the currents are equal in this particular branch. So then, writing the KCL equation at this particular node, we will get equation for IA as IA is equals to ISH plus IL. So we need to find ISH, as we already have IL in the given question. So we need to find ISH now. ISH will be nothing but VSH by RSH. To write the equation for VSH, so we need to write the equation for EG. EG for this particular type of generated EMF will be given as now IA into RA plus RSC plus the brush drop. So when we write a KVL equation in this particular loop, we know that the generated EMF is coming from the armature. So when we write for this particular loop here, we get this particular equation. So from this, we need to write the equation for, so ISH can be calculated as EG minus IA into RA plus RSC minus VBD divided by RSH. So now he has directly given our terminal voltage as 500 volts. So this particular voltage is now taken as 500 volts and RSH value is 250. So we will get it as 2 amperes. So from here, as IL is 50 and ISH is 2, we get our armature current as 52 amperes. So we got the armature current now. So now we need to find out the induced EMF in long shunt machine. So to find out induced EMF in a long shunt machine, we need to write the induced EMF or generated EMF equation. So I'm writing generated EMF equation for this particular long shunt generator, long shunt compound generator. So we will get IA into RSC plus the brush drop. So VT he has given us 500. We got IA value as 52. Then we will add RA plus RSC 0.05 plus 0.03 plus the brush drop is 2 volts. So we will get EG value here after calculating it further. So this is how you calculate the generated EMF for long shunt compound generator. Then moving again, calculating it for the short shunt compound generator. Now assuming the case of short shunt compound generator, we need to first draw the circuit. Short Short shunt compound generator is a generator in which the shunt field winding is only connected across the armature terminals. And apart from this, we have series field winding. So here we have again RA is the resistance across the armature, RSH is the shunt field resistance, and RSC is the series field resistance. Again, your armature will be delivering the current IA to shunt field current and to the load. So from this, if we apply KCL at this particular node, we again get the current equation as IA is equals to IL plus ISH. So to calculate ISH now, we need to find out ISH is the only voltage which is being reflected across the armature terminals. As we have the shunt field winding only connected across the armature terminals, so we need to write, which is nothing but VSH by RSH. This VSH will now be EG minus IA, or we can simply write it as, first let us write the equation for EG. So when I write EG equation or the generated EMF equation for this particular loop here, I will get it as V, that is nothing but the voltage across the load, terminal voltage, plus the current which is flowing in armature conductors, plus ISC, RSC. Plus we also have the brush drop. So from this, here VT is given as 500 volts. So now we need to calculate ISH first. So to calculate ISH again, we have 500 volts, which is the terminal voltage which is being applied across the load terminals. And we have load current as IL as 50 amperes. So we need to calculate ISH such that we will get IA value. So now to calculate IA value, we have VSH by RSH. So VSH will be now generated EMF EG minus IA RA minus ISC RSC minus VBD. So we are now coming to a conclusion that terminal voltage, we have already calculated the armature current in the previous case. So we have got the shunt current as VSH by RSH this VSH is 500 by 250, so we will get it as 2 amperes. Again, we got it as 52 amperes. So VT is given in the question. We know that now IL is equals to ISC because the series field winding and the load are connected in series. So now IL will be equals to ISC. So IA is 52 amperes, 52 multiplied by 0.05 plus ISC. ISC is nothing but, now it's load current. So we take it as 50 multiplied by RSC 0.03 plus the brush drop is 2 volts. So upon calculating this term, we will get the induced EMF for short shunt compound generator. This is how we analyze or find out the induced EMF for different kind of generators, that is, it may be series, shunt or compound generator. Moving on to the next problem, we have a numerical on separately excited generator. We know that separately excited generator is nothing but when a field winding is excited separately by a DC source, then that kind of generator is called as separately excited generator. So this is nothing but the supply which is given to the field winding. The current flowing here can be taken as field current, and we have again RA. EG is generated here. This is the load, and we know that IA will be delivered to the load and the terminal voltage VT. So now, given data in the question, let us list out the given data in the question. He has given the speed as 500 RPM. He has given it delivers 120. So we can take the armature delivers 120 amperes to the load. So I can consider this as the armature current at 500 volts. So the load voltage is also given as 500 volts now, at which speed the current will be reduced to 60 amperes, and armature resistance is given as 0.1 ohms. It is not watts, it is ohms. He has also given our brush drop. We know that as there are 2 brushes, so drop across each brush multiplied by 2 will be given as 2 volts. So now writing the equation, he is asking us to find out the speed at which the current will be reduced to 60 amperes. Now it is 120. He is asking us to find out the speed at which the current will be reduced to 60. So for that, we need to find out EG. So EG for the first case, which is nothing but V plus IA RA plus VBD. So now armature is delivering the current, it is taken as armature current, 120 amperes. So he has given 500 volts, current is 120 and the resistance is 0.1 and the brush drop is 2 volts. So we can take it as 500 plus 12 plus 2, which is nothing but 514 volts. This is EG1 when IA is equals to 120 amps. Now calculating EG2 using the same equation, but the current will now become 60 amperes. It is again 500 plus your current, now it will be 60 amperes multiplied by the resistance 0.1 ohms multiplied by added to brush drop, that is 2 volts. So we get here as 500 plus 6 plus 2, which is nothing but 508 volts. So we got our EG1 as 514 volts and EG2 as 508 volts. So from this, we have the equation for speed. You know that EG equals to pi ZNP by 60A. From this, we can take the direct proportional relation between the speed and EG. So from this, I can write EG1 by EG2 is equals to N1 by N2. I got 514 divided by 508. The speed is given in the initial case as 500. I need to find out N2. So from this, we can get the value of N2. So this is how we calculate the speed for different values of armature current at different situations for a separately excited generator. So that's it about the numericals on different types of generators. Thank you.